Today we will be learning about the constitutive equations of orthotropic composite materials. This video is prepared by Melda Kuzelton, Carson Bay, Patrick Kim, and Shahir Rana. We're going to break the intro into three different sections: composite materials, orthotropic materials, and then composite orthotropic materials. They're really useful. They're used in everything you can imagine, from kayaks to spaceships, depending on the application. So to define a composite material, it's a material made up of two or more other materials. This combination then gives the resulting composite unique and often better material properties. Sometimes it's done to increase strength per unit length or have better thermal properties. The possibilities are really endless. Composites are generally made up of two different sections. There is a reinforcement and a matrix, which then combine to create the composite. The reinforcement can come in many forms, as shown in the bottom picture over here. Different kinds of reinforcement embedded or fused within the matrix gives them different material properties. For example, one type may be particularly useful for distributed loads, while another type might be particularly useful for compressive point loads. A popular example of a composite material is fiberglass. In this case, the reinforcement is glass, which is embedded into a matrix of thermoset polymer. Both the reinforcement and the matrix can be different kinds of materials depending on the application. The picture on the left shows the different kinds of glass reinforcement that can be used. Moving on to the orthotropic materials, they're defined as materials whose mechanical or thermal properties are different in three mutually perpendicular directions, meaning that if a material is compressed along each of these directions, the result will be different. One direction may be easily susceptible to compressive forces, whereas another direction may be incredibly resistant to compressive forces. Some examples of orthotropic materials include wood, rolled metals, and many different crystals. This is often due to their internal grain alignment, and depending on the angle of applied force, the material will react differently. Now, knowing the definition of composite materials and orthotropic materials, we can combine them to understand what composite orthotropic materials are. It's simply a composite material whose mechanical or thermal properties are different in three mutually perpendicular directions. This generally happens when the composite reinforcement is parallel or layered into the matrix. This creates the axes of symmetry. Some examples of this are fiberglass, laminate, and carbon fiber laminate. The picture here shows a piece of aerospace-grade carbon fiber epoxy laminate. This is special because it's a composite of carbon fiber and epoxy, carbon fiber being the reinforcement and epoxy being the matrix, and then it's laminated by stacking slabs of this on top of each other, which most likely in different directions, to become an orthotropic material. With that intro done, we move on to the theory behind it.
Thanks, Melda, for the introduction. So as promised, the purpose of today's lecture was to discuss the constitutive equations of orthotropic composite materials. What that really means is we're just going to be applying Hooke's law to stress and strain in materials, as well as the shear stress and the shear strain in materials in each axis. However, let's first look at the general case of Hooke's law, that is, how it pertains to isotropic materials. So isotropic materials are really nice in the sense that they're a simplified version of the orthotropic equivalent. They allow us to develop basic constitutive stress equations that we can then modify to apply to orthotropic equivalents. So, in terms of context, the isotropic solid is just a three-dimensional object with uniform mechanical properties. What this means is that the mechanical constants, such as Young's modulus, Poisson's ratio, and as well as others such as thermal and electromagnetic constants, do not vary with direction. So, let's first look at the stress equations for isotropic solids, and we'll be calculating the normal strain in each orthonormal axis. So, some assumptions and requirements that we'll have to make in order for the equations to hold true is that the strain effects are small enough to not impact load application in other axes. For example, if I have a force being applied in the x direction, the deformation will not impact the load application in the z-axis. You'll see why in the diagram in the next slide. Additionally, we need to make sure that there's a linear relationship between stress and strain. What this means is that we're only interested in the elastic deformation portion of the stress-strain curve. This is why the constitutive equations fail for plastic deformation, because the linear relationship no longer applies. You'll see this in the stress and strain curve on the next slide. There are four parameters that we'll need to develop these equations for the isotropic solids. We have the two constants, the Young's modulus and the Poisson's ratio, and then the stress and strain. So here we have a nice equation for the generalized Hooke's law. With it, you can calculate the strain in each axis using the Young's modulus, the Poisson's ratio, and then the stress being applied in each axis. You have three cases: one-dimensional, two-dimensional, and three-dimensional loading. In the cases where you have less than 3 dimensions, the other stress applications would be zero. And with it, this is really important because as it pertains to Poisson's ratio, when one axis is being deformed, the other two axes will also be deformed. So in the case of a cube, when a force is being applied across the x-axis, you'll notice that it's lengthening because the volume of that cube needs to remain constant even when it's deformed. The other two sides will compress, and this is because the volume needs to remain constant. However, because this is an isotropic solid, the mechanical properties are the same. And this also means that the Poisson's ratio is the same. So the y-axis and the x-axis or the y-axis and the z-axis will compress by the same amount, meaning the Poisson's ratio is the same for each of them. So the cross-sectional area will remain a square, even though the x-axis is transforming into a rectangle. So the Poisson's ratio is the same no matter of whether it's being applied in the x, y, or z axes. And then finally, the Young's modulus is also the same throughout the object. And this is just found from the material stress strain curve. And you can obtain this by taking the slope of this linear region, in other words, the stress over the strain. So let's move into the shear strain equations for isotropic solids. We'll talk more about how this differs from the regular stress and strain equations in the next slide. So the context is exactly the same. You still have the same object with uniform mechanical properties subject to multi-axial loading. The purpose is different in the sense that we now want to obtain the shear strain or stress in each orthonormal axis, and the requirements and assumptions are also the same as before. We have a new set of parameters. Now we're interested in the shear stress. We are now interested in the shear strain, which is measured in radians. And we also have a new modulus, which is the modulus of rigidity. So here's the shear stress equation. All you need is a scaling factor, or the modulus of rigidity, to easily convert between shear stress and shear strain in each axis. And you can easily calculate the modulus of rigidity using Young's modulus as well as Poisson's ratio. So in the end, regardless of whether you're calculating the shear stress and strain or the regular stress and strain, it all comes back down to having access to those two key material constants, the Young's modulus and the Poisson's ratio. You'll notice in the diagram on the right, as force is being applied in the axis that's parallel to the desk, the actual square is being deformed into a rhombus. You'll notice that the deformation is measured in angles. This is because the actual side length of the object remains the same. However, there is deformation between the bottom left corner and the top left corner. This deformation or difference can be measured in length. However, with this equation, it's instead represented as an angular difference in radians. So here's what we learned about isotropic materials. We have three equations for strain, one for each axis, three equations for shear stress, one in each axis, and then we have three constants: the Young's modulus as calculated from stress and strain, the Poisson's ratio as calculated from deformation in the lateral and axial axes, and finally the modulus of rigidity as it's calculated from the Young's modulus and the Poisson's ratio. The key thing to remember is that there's only one of each constant for the isotropic materials, as they have uniform mechanical properties that do not vary with direction.
So those are the equations for the isotropic material, but what if the solid was orthotropic, such as carbon fiber? Well, then the original constitutive equations will not work. This is because orthotropic materials have different properties for each x, y, and z direction. So the same stress in each direction will result in a different elongation on each side. Take this object on the right, for example. If this object were to be isotropic, the axial load on the x direction would lead in a same amount of compression on the y and the z axis, which would result in a square cross-sectional area. If it were to be orthotropic, however, this axial stress would cause a different amount of compression from y and z axis. So for example, the y-axis might compress more than the z-axis, which will result in a rectangular cross-sectional area. Now by definition, different mechanical properties would lead to a unique Poisson's ratio and modulus elasticity depending on the x, y, z axis, and thus unique strain expressions for each axis. Now recall that for Poisson's ratio, it is negative of lateral strain over axial strain. And for isotropic materials, the Poisson's ratio of x, y would equal Poisson ratio of x, z would equal Poisson like v of y, z. Because obviously in an isotropic solid, compression on one side would lead to like the same elongation on the other sides. But this is not necessarily true for orthotropic. As mentioned earlier, when there's like a load, an axial load in orthotropic materials, the compression on the y-axis and the compression on the z-axis are not equal. So the ratio, or Poisson's ratio, differs for every single possible combination of the x, y, z axis and its compression. So in order for us to derive the questions and the equations, we need to specify which Poisson's ratio we're talking about. For example, v of xy, meaning the plane that's perpendicular to the x-axis and the elongation being the y, sorry, the compression being the y, would equal negative of the lateral strain in this case is in y direction, and the axial strain would be the strain in the x-axis. Similarly, the Poisson's ratio xz would equal to negative of the strain in the z-axis this time, that's a lateral direction we're talking about, divided by the axial strain, which is x-axis. So knowing this, let's try to derive the strain for orthotropic materials from the equation that we derived for the isotropic materials. So here's the original equations for the strain from the isotropic materials. Let's expand the v over e term back into the brackets, which will result in this expression for the strain. Now, notice that the Poisson's ratio does not have a suffix because it was generalized and this was okay for isotropic, but it is not in orthotropic. We need to specify the direction because the properties are different and the values are different for each direction. This is also true for Young's modulus. Young's modulus in x direction is not equal to Young's modulus in y direction, is not equal to Young's modulus in z direction. So we do specify that for the orthotropic materials. So for example, the strain in x would be the stress in x divided by Young's modulus in x direction minus v of yx, the Poisson's ratio, multiplied by stress in y direction divided by the Young's modulus in y direction minus the Poisson's ratio zx multiplied by stress in z direction divided by Young's modulus in z direction. And it is the same situation for stress in y, strain in y and strain in z. The expression's order has been swapped a little to get the x term first, followed by the y terms, and then the z term. So as you can see, this applies for all three expressions, where the Young's modulus and the Poisson's ratios directions are specified, because they are different. This is similar for shear strain as well. In the original equations for isotropic materials, we had that the shear strain of xy would be tau xy, the shear stress divided by the modulus of rigidity, or shear modulus. And it would be the same for shear strain yz. It would be tau over yz over modulus of rigidity. And in an isotropic material, the modulus of rigidity was the same. This is not, again, not true in orthotropic materials, where each orthogonal direction has a different property. So once again, we have to specify which modulus of rigidity we are using. So once again, the G has a suffix now. For example, for the shear strain in xy, you would get tau xy divided by G in xy, and it's the same case for the other two. So combining these three expressions with the one we derived from the last one, we get the constitutive equations for orthotropic composite materials. And here are the 6 equations. These are very similar, almost identical to the isotropic equations, but once again, the Poisson's ratio, the Young's modulus, and modulus of rigidity have their own directions because they are not equal when it comes to their values depending on their direction.
And to finish off, we're going to do a quick example problem. A 60 millimeter cube is made up from layers of graphite epoxy with fibers aligned in the x direction. The cube is subjected to a compressive load of 140 kilonewtons in the x direction. The properties of the composite material are as follows. Determine the changes in the cube dimensions, knowing that 1. The cube is free to expand in the y and z directions, or the cube is free to expand in the z direction but is restrained from expanding in the y direction by 2 fixed frictionless plates. First, we're going to deal with the cube being free both in the y and z directions. To start off, we determine the stress in the direction of loading, which is done normally with pressure over area or force over area, which gives us a negative 38.89 megapascals. With the cube unrestrained in both the y and z, the stress in those directions equal to 0. This reduces our early equations down to the equations that you see down here. We get a much higher strain in the x direction due to the lack of scaling due to the isotropic material properties. As you can see there, we have negative 250.9 times 10 to the negative 6 for the strain in the x direction, and positive 62.22 times 10 to the negative 6 in the y and z directions. The corresponding changes to the cube dimensions are calculated as normal by strain times the original length of the cube, which gives us negative 15 micrometers of compression in the x direction and positive 3.73 micrometers expansion in the y and z directions. Moving on to B, where we have the cube free in the z direction but restrained in the y direction. With the strengths in the y direction, the strain in y must equal 0, and as such, the stress in y cannot equal 0. Stress can be solved using the earlier equations, sorted around to solve for stress in y, which comes out to negative 752.9 kilopascals. With that, we want to move forward to solving the strains, but before we can do that, we'll need to solve for Vy of x, which does not equal Vx of y that is given due to the material properties. That is solved using the ratio as follows, which gives us a very small number of 0.01936. Moving on, we can then calculate the strain in the x and z. Strain in y is 0, obviously, and so because of the added stress in y, a few more terms are added to both of our equations. As you can see here and here, and those plug in all the numbers equal to negative 249.7 times 10 to the negative 6 and positive 90.72 times 10 to the negative 6. Changes in the cube direction dimensions are calculated as normal, negative 14.98 micrometers and positive 5.44 micrometers. You can see here there's quite a difference between how much compression is going on in the x direction and how much expansion in the z, which is due to the reinforcement in the laminate material. Thank you so much.